So now I want to get into a topic of stability in aromaticity. So firstly, I just am gonna show you a series of, let us say, there is a branch of aromaticity that we are currently studying, and it relates to cyclic compounds. So we have cyclic compounds here. Now, cyclic compounds which follows cyclic resonance are the ones which we have been looking out for. So now when this cyclic resonance occurs, the compounds can become extra stable or they can become extra unstable. Now, when they become extra stable, they become aromatic, as we have been telling ourselves that aromatic compounds are very, very stable. So, what is the condition of aromaticity which differs it is 4n plus 2 is, let us take it as x, and this n has to be a whole number. So, here we go. So, extra stable are aromatic. Now, we have got a category of extra unstable also, and these are what we call as anti-aromatic compounds. So the anti-aromatic compounds are the one which are extra unstable. So we have got a condition for it also, that 4n, assuming it is x, and this n begins from 1, so they are natural numbers. So we have got ourselves two categories inside aromaticity, where one of them is extra stable, one of them is extra unstable, and we have got ourselves aromatic and anti-aromatic at two ends of the stability scale. Now, if I write the order of stability, now I want to generalize this order of stability so that I have a good idea about when to call a compound very, very stable and when not to. So the orderability, since aromatic are extra stable, so they come first, followed by non-aromatic compounds. They are the ones which do not follow the aromatic conditions, the conditions of aromaticity. And then after the non-aromatic, we have the anti-aromatic, because they are the extra unstable ones. So we have anti-aromatic. There's a thin line between aromatic and anti-aromatic. So a thin line can make a compound extra stable or extra unstable. That is depending upon the Huckel's rule. So we have got ourselves order of stability that we wanted, a generalized order of stability which says that aromatic becomes greater than non-aromatic and this becomes greater than anti-aromatic. So we have to remember this order whenever we are solving any question so that we have an idea about the stability that we are going to achieve. Now here in this next example, I wanted to show the effect that aromaticity has. So this is a question which says that we have to tell which reaction is feasible. Now, since AgNO3 is present here, we know that whenever AgNO3 is present along with Cl, we obtain AgCl. So in both of them, we'll obtain AgCl. But now I have to tell whether which one of them will be feasible and the reaction is gonna go forward. So if I'm removing a Cl, of course I'm breaking this bond here. Okay, and we're gonna sever this bond. Now what happens is when I am gonna break this bond, there are gonna be some charges developing on them. So we're just gonna write that since chlorine is an electronegative atom, it takes the negative charge. So it has a greater tendency to pull the negative charge toward itself. And what I obtain is that here it is going to take the negative charge with it, leaving behind a trail of positive charge for us. So we have got a positive charge here and a positive charge here. So what I'm going to achieve if I complete this reaction here is that here I have got this with a positive sign because a positive charge is left, and here I have got the same one with a pi bond and a positive charge here. So now to check the feasibility, I have to compare the stability of these two that I have just obtained. So if I look at this one, the first one, let's call this the first, and this, let us call this the second one. So if I look at the first one, what I see that it is, one look at it and I'm sure that it is not planar because I have here this space here, which is of course sp3 hybridized, and we know that it cannot be planar at all. So it is not satisfying conditions of aromaticity, and we have no reason to call it anti-aromatic, so it becomes non-aromatic. Okay, so this becomes non-aromatic. Now coming to the second one, I see here that I have got a positive charge here and I have got a pi bond here. So how many pi electrons do I have actually with me? I have got only 2 pi electrons because we only count these pi electrons. So the positive charge does not contribute anything for us. Okay, so I have got 2 pi electrons with me now. I check the Huckel's rule, 4n plus 2. I have got I check 4n plus 2 is equals to 2, and I've got that n is equals to 0. So this follows the first, it follows Huckel's rule. Second one, so Huckel's rule is a go for us. The first one it follows. Now I come to the second condition and I see this is a carbocation. Of course it is sp2 from this side, and the rest of the two carbons are also sp2, so or are sp2, and this becomes planar. The third condition which I have is that it should be cyclic, and I can see clearly that it is cyclic because it is closed. So this one, the second one, becomes aromatic. Yes. So this one is aromatic. And I know if something becomes aromatic, it becomes very, very stable. So I can say that the second reaction is feasible because we obtain an aromatic species, which is very clear from the above explanation that we have just done. So, if I have to say which one is feasible, so this reaction is not feasible and this one is feasible. So, the second one, the second reaction is the one which is feasible because it leads to the formation of an aromatic species, and we know that wherever there is aromaticity, there is stability. So we can easily see how the answer is the second reaction, which is feasible.